Okay, so in this function, we're going to, not this function, in this video, we're going to talk about graphing rational functions. So we are going to use stuff that we talked about in the previous videos about horizontal and vertical asymptotes. Now, a lot of textbooks have kind of a guideline for graphing them. I'm going to set my own up here because oftentimes I find that some of the guidelines that they use um, don't really give all of the story here, or in my opinion, leave something very important out. So these are guidelines, and I am going to put them in an order here. And when I say guidelines, the reason we say guidelines is because it's not a harsh that you have to do it this way every single time, but it's kind of like this set will kind of give us all the information that we really kind of need here. So what I'm going to first do here is the first thing I'm going to say is find the domain of f of x, because we need to know what points there's either going to be nothing plotted, holes, or, well, again, these are possible vertical asymptotes. Then the next thing I like to do is go ahead and find vertical and horizontal asymptotes. And then I like to find x and y intercepts. Now this is where the guidelines kind of come into play here. You can kind of do some of these in any order. You don't have to find the vertical and horizontal asymptotes first. You could find the x and y intercepts first. That'd be fine. It doesn't matter. And then what are we going to do here? Well, next thing we'll do is sketch and plot the information above. And then plot a few additional points to ensure behavior. And then 6, sketch the graph. Now one thing before we do an example here, let's talk about vertical asymptotes again. Remember how we had multiplicity with zeros? We also have multiplicities with vertical asymptotes. If the multiplicity of a vertical asymptote is odd, then you go to infinity on one side and negative infinity on the other side. If the multiplicity of a vertical asymptote is even, then both sides go to infinity or negative infinity. Alright, so, and we're going to also talk about the multiplicity of the zeros, because the same thing applies with these rational functions, where if you have an odd multiplicity of a zero, you go through the x-axis, where if you have an even multiplicity of the zero, you would touch the axis. So let's just look at an example here. So let's look at f at x equals 3 plus 2x over x plus 1. Alright, so let's go ahead and sketch the graph of this. Now before I even bring up the graph here, we're going to go ahead and find a bunch of information. So again, I always find the domain first, and I have x plus 1 in the denominator, so there's not really even a lot of work to do this. I could just say it's all real except whatever makes the denominator 0, and in this case it's pretty obvious, x equals -1. Now I'm going to go ahead and find horizontal and vertical asymptotes. So let's rewrite this as 2x plus 3 over x plus 1. Well, this doesn't reduce. So it doesn't reduce, so I don't want to do anything with, there's nothing I can do with that. And then that also tells me then x plus 1 equals 0, then x equals -1 is a vertical asymptote. And then if I want to talk about horizontal asymptotes, I look at my lead terms. Of course, the lead terms are 2x and x. So the end behavior follows 2x over x, which is 2. So y equals 2 is a horizontal asymptote. And then let's go ahead and find x and y intercepts. Well, x intercepts are when my numerator is 0. So I want to know when 2x plus 3 equals 0. And of course, then I'd have 2x equals -3. So x is -3 over 2, which is also the same thing as -1.5. So this is x-intercept of -1.5 comma 0. And then if I want to do a y-intercept, my y-intercept would be f at 0, substitute 0 in, so this would be 2 times 0 plus 3 over 0 plus 1, which of course is just 3, and so this would be a y-intercept. Now I'll go ahead and put this information in here so I know, because I am going to need to plot a couple extra points, but until I have some of this drawn here, I don't know what the extra points are that I need to plot. So let's go ahead and get a graph going here. Alright, now let's bring this down a little bit here. There we go. Alright, so here's our graph, and let's go ahead and plot in some of this information here. So again, I'll scroll up a little bit here. We have x equals -1 is a vertical asymptote, and y equals 2 is a horizontal. So at x equals -1, I'm going to do a dotted line here to represent my vertical asymptote. Y equals 2, I'm going to do a dotted line to represent my horizontal asymptote. And then I'm also going to plot in the x-intercept and the y-intercept. So I have a y-intercept of 3, so I'll plot that here. That would be right here. And then I have an x-intercept of -1.5, so that would be right here. So I have a point there. Now, as I said, plot a couple extra points here just to kind of get some of the behavior here. And I would say plot a minimum of 1 point in each of these quadrant areas here by the horizontal asymptote. Sometimes you might want to plot 2 in there, but we'll go ahead and just do 1. So I need to plot another point in here. Well, I'm going to pick an easy number since I have x equals 0. Why don't I just figure out what f at 1 is? So f at 1 would be 2 times 1 plus 3 over 1 plus 1. So this would be 5 over 1, or 5 over 2, which would be 2.5. So that would mean that here's a point roughly right here. And then we could do the same thing here. Let's just go ahead and do, instead of -2, let's do -3. So f at -3 would be 2 times -3 plus 3 over -3 plus 1. So this would be 2 times -3, -6 plus 3. That would be -3 over -2, which is positive 1.5. So at -3, I'm at 1.5, which is right here. Now I know I need to go towards the horizontal asymptote, so I can see right now, and these are going to be smooth, it's going to be like this. Now, I didn't write the multiplicities down, but let's make sure that these multiplicities make sense. The 0 had a multiplicity of 1, which means I go through it, and the vertical asymptote had a multiplicity of 1, which is odd, which means one side's going to -infinity, which is down here, and one side's going to positive infinity, which is up here. Alright, so let's look at another one of these. Let's look at h at x is equal to 2 over x squared x minus 2. Alright, so let's go ahead and start here. Well, the domain here is going to be, well, again, this is kind of already factored here, so it's kind of obvious to me. You might have to factor on some of these problems, but this one it's not needed. So it's all r except x equals 0 and x equals 2. Now let's talk about vertical and horizontal asymptotes. So vertical asymptotes, well, this clearly doesn't reduce any, so this is going to be when x squared is equal to 0, or when x minus 2 equals 0. Well, this gets me x equals 0 and 2. But we have multiplicity here. The x equals 0 is multiplicity 2, and the x equals 2 is multiplicity 1. So now these, remember, are my vertical asymptotes. Alright, so then let's look at the horizontal asymptote. Well, it follows the lead terms. Now you might say there's no lead term in the numerator. There absolutely is. The lead term is the only thing there, which is 2. And then we have to be careful. The denominator, the lead term isn't x squared. You would want to rewrite this as 2 over x cubed minus 2x squared. And so the lead term in the denominator is x cubed. Now, in this particular example, it wouldn't make a difference, but it does make a difference in some problems. So then my end behavior follows 2 over x cubed, and we talked about this in one of the previous videos, that if you have 2 over x cubed, as you go to infinity or as you go to negative infinity, this is going to go to 0 as x goes to infinity or x goes to negative infinity. So we get y equals 0 as a horizontal asymptote. Alright, well, now we're supposed to do y-intercepts and x-intercepts. Well, unfortunately I can't do either of those because there are no x-intercepts, because if you look back here, there's nothing that's going to make the numerator 0. And as far as y-intercepts, well, there can't be a y-intercept. One of the reasons there can't be is because, well, 0 is not in the domain, or you can think of it as that one of your vertical asymptotes is 0. So there's no x-intercepts or y-intercepts. So at this point, we can sketch the graph that we have, which is essentially nothing, but we'll go ahead and at least put in the horizontal and vertical asymptotes. Alright, so we have horizontal asymptote of x equals 0. So I'm going to kind of do some kind of slashes here to represent that. Now we want to remember that's multiplicity 2, and then we also had a vertical asymptote of x equals 2. Okay, now we have a horizontal asymptote of y equals 0, so that's this horizontal line right here. So now I literally have no points, so I am going to have to plug in some points here to find some things out here. So let's go ahead and start with some of the negative ones here. So let's start with y equals -1. So let's go ahead and do f at -1, and this would be 2 over -1 squared -1 minus 2, yeah, which would be 2 over -3. So it's -2/3. So, you know, again, we're going to have to kind of rough sketch this here. So -2/3, -1, kind of like right there. All right, so let's do another one here. Let's maybe do, let's do f equals -1/2. And so this would be 2 times -1/2 squared times -1/2 minus 2. So this is going to be 2 over 1/4 times -2.5. Now I'll go ahead and use a calculator to evaluate this because I'm going to want to plot this. So 2 divided by 1/4 and then -2.5. And you get that this is -3.2. Alright, so -1/2 is roughly right here. So then 1, 2, -3.2. So 3, and so it's going to be a little bit over, so maybe like right there. And again, that's enough to get us started here. So, and in fact, technically, I can sketch it without any more information here, and I'll show you how. Because once I have this here, I know, well, excuse me, I've got my horizontal asymptote like this, and then I know that this is going to come down and go to the vertical asymptote. But then what else do I know? I know that the multiplicity of this vertical asymptote here at x equals 0 is 2, which means it has to come here. And then what do I know? There's no x-intercepts, so I can't touch the x-axis, so it's going to come up. Now I don't know how far. I'm just going to sketch this because again these are sketches, so it's going to come up a little bit, but then it has to turn and go back down because there's no x-intercepts, and I have to go to either positive and negative infinity on this vertical asymptote here. Well, then what's the multiplicity of this one? Well, the multiplicity of this line here is odd, which means then I'm going to be up here, which then can finally say, well, that means I know I need to go something like this. So I actually only plotted 2 points, and that was enough for me to get a rough sketch here. Now, if we want to be a little bit more precise, we could, but as far as being able to get a rough sketch of the graph, this would give us a rough sketch of the behavior of the graph. And as said, to be a little bit more accurate, for instance, we could substitute the number 3 in and see what we actually get at f at 3. And so this would be 2 over 3 squared times 1 minus 2, or I'm sorry, not 1 minus 2, times 3 minus 2, which would be 2 over 9 times 1, which is 2/9. And we can see how my graph isn't very accurate in that sense because, look, I have it going at 1 here at x equals 3. So it really, if I want to erase this here a little bit, to be a little bit more accurate, 2/9 would be kind of down here. And so the graph is going to go something like this instead. But what I'm going to be most interested in is having a few points plotted and having the behavior be roughly correct. Okay, so let's look at one more example. And this is going to be an example where we're going to actually reduce the thing down, because again, we're going to look for vertical asymptotes. And so this is going to be looking at the function f at x equals x squared minus 36 over x plus 6. So again, the domain here, as we can see just here, it's all real except x equals negative 6. Okay, so then let's look at horizontal and vertical asymptotes. Well, vertical asymptotes, remember, we should always reduce this down. The other two examples we didn't have anything to worry about because it clearly didn't reduce, but x squared minus 36 clearly factors to x minus 6 over x plus 6 divided by x plus 6. And this reduces down to, of course, just x minus 6 over 1. Now, what I want to emphasize is the graph of f at x behaves like x minus 6, except we are not defined at x equals negative 6, because that's not in the domain of the original function. Now, it's absolutely what the graph is going to look like. It's going to look like x minus 6, but it's not defined at x equals negative 6. So what does that mean? We are going to have a hole at x equals negative 6. All right. So there's no vertical asymptotes. And we can also see if the graph behaves like x minus 6, there's also no horizontal asymptotes. And x minus 6, there's not really like, oh, I could find the x and y intercepts, but I already know what that graph is going to look like. That's just a straight line. Now, as I said though, it's a straight line except we're not defined at x equals negative 6. So I'm going to go ahead and I'm going to change this here, and I'm going to do these by 2's here. So let's do negative 2, negative 4, negative 6, negative 2, negative 4, negative 6, negative 8, negative 10, and then I am going to continue this down and go to negative 12. And the reason is okay, well, x minus 6, well, that's just a straight line with a y-intercept of negative 6 and a slope of 1. So I mean, those are some points here that I could plot, and I could draw a line, but it's not defined at x equals negative 6. So we want to ask ourselves, what does x minus 6 equal when x is negative 6? Because I know that point's not going to be there because it's not in the domain of f at x. Okay, well, we just put in negative 6 minus 6. This is negative 12. And I simply go ahead and, instead of putting a point there, negative 6, negative 12, there's a hole there because that's not defined. So we put a circle there. And yeah, my circle's a little bit big and elaborate, but the idea is then, well, I would draw a straight line here and then continues this way. So the graph of this rational function actually looks like a straight line, but it's got a hole in it. So that's what can be very kind of tricky about rational functions, is the graphs can look kind of like anything here. So just has to take practice of getting used to these.